Hey. 42. Here. What if instead of cutting your eye open to fix your vision, we just added to it? That's not science fiction. That's where eye surgery is right now. And nobody is talking about it. Here's the problem with how we fix eyes today. Cataracts. The lens inside your eye clouds over. The fix. Cut it out entirely. Replace it with a plastic lens. You're essentially running your eye on hardware from 1949. The implantable lens was invented in 1949. We've barely changed the concept since. LASIK. Your cornea, the clear dome on the front of your eye, is too curved or not curved enough. The fix? Burn away tissue with a laser until the shape is right. You cannot add tissue back. Whatever they remove is gone forever. 20% of people are disqualified because their corneas are already too thin to safely remove more. Both of these are subtraction surgeries. Remove the problem. What the field is now asking is, what if you could add instead? The cornea is the front window of your eye. 5 layers. The one that matters for vision is the stroma. 500 microns thick, made of collagen fibrils arranged in 300 lamellae running in alternating directions. The whole structure is essentially a biological optical fiber. Here's what makes it transparent. The collagen fibrils are exactly 25 to 32 nanometers in diameter. They're spaced exactly 62 nanometers apart, center to center. That precision causes scattered light to destructively interfere, canceling itself out, leaving only straight transmitted light. Move those fibrils even slightly and you get scar tissue. Opacity. The biology is doing optical engineering at the nanometer scale. Any additive approach to corneal surgery has to respect this. You can't just inject filler. You have to reproduce the architecture. In 2022, a team in Sweden published something remarkable in Nature Biotechnology. Mehrdad Rafat at Linköping University had spent years developing a material from porcine collagen, pig skin specifically, the kind used as a byproduct in the food industry. He purified it, cross-linked it twice, once chemically, once with UV light, and produced a completely transparent hydrogel implant with no living cells inside it. They called it BPCDX. They implanted it into 20 patients. Not patients with mild vision problems. Patients with advanced keratoconus, a condition where the cornea thins and bulges outward until you're legally blind. 14 of the 20 patients were legally blind before the surgery. The surgery took minutes. A femtosecond laser cut a tiny pocket inside the cornea. No stitches, no full incision. The implant slid in. The pocket closed on its own. At 24 months, 0 rejections. 0 adverse events. 8 patients who had been legally blind had their sight restored. 3 achieved 20/20. They needed 8 weeks of immunosuppressive eye drops instead of the years required after a conventional corneal transplant. This implant is made from pig collagen. It is completely cell-free. It integrates into your cornea. Your immune system largely ignores it. That is additive surgery. You are building up a thinning cornea instead of removing from it. At the same time, a company called Precise Bio built something different. Instead of a cell-free implant, they wanted living tissue. They took donor corneal endothelial cells, the cells lining the back of the cornea that maintain its hydration, and therefore its transparency, expanded them in culture, and printed them into a sheet using a robotic biofabrication system. One donor cornea becomes 300 printed implants. In October 2025, they implanted the world's first 3D bioprinted living corneal implant into a human patient at Rambam Medical Center in Israel. Results are expected in 2026. Now here's the question that doesn't have an answer yet. Can you implant synthetic corneal tissue and then use a laser to sculpt it to your exact prescription? This is the logical next step. The BPCDX implant builds up a thinned cornea. What if instead of implanting a pre-shaped disc, You implanted a blank layer of synthetic stroma and then used an excimer laser. The same laser used in LASIK, to cut it to exactly the right shape for your eye. People who were disqualified from LASIK because their corneas are too thin could get synthetic tissue added first. Then LASIK. Their corneal bank account refilled before the withdrawal. Here's what we know. The excimer laser at 193 nanometers does ablate synthetic hydrogels. The ablation rate is close to native cornea, about 0.4 microns per pulse. But it varies with water content. Current hydrogel implants have a refractive index of 1.334. Native cornea is 1.376. That gap creates an optical interface at the implant boundary, scattered light aberrations. The LASIK algorithm calibrated for native tissue would cut the wrong amount. 0 published studies have tested this. The concept exists only in theoretical discussion. The other problem, the synthetic tissue doesn't have the nanometer scale collagen organization of native cornea. The excimer laser ablates cleanly through native lamellae. In a hydrogel with no lamellar structure, the ablation edge might not be as clean. No one knows. There's a third approach that doesn't remove anything, doesn't add anything, just changes what's already there. LASIK. Laser-induced refractive index change. Developed at the University of Rochester by Scott McRae and Crystal Huxland. A femtosecond laser at 405 nanometers. Low energy, non-ablative, fires pulses into the corneal stroma. Each pulse densifies collagen fibrils at the focal point, raising the local refractive index. By writing a three-dimensional pattern of refractive index changes through the cornea, you create a lens inside the tissue. No cutting, no removal, no addition. Pure optical modification. First human trial was 2018. 27 patients. Presbyopia correction. At 3 months, no inflammation, no haze, no endothelial damage. Some improvement in near vision. A 2022 trial showed statistically significant reduction in refractive error with improved contrast sensitivity. The same company, Clariovision, is now pursuing regulatory approval in Europe. A related company, Perfect Lens, applies the same concept to artificial lenses already inside the eye after cataract surgery. Use a femtosecond laser to modify the refractive index of the implanted plastic lens post-operatively. Your prescription changes over time? Go back to the clinic. Get a square update for your eye. Here's the thing that connects all of this. Right now, if you get LASIK and your prescription changes 5 years later, there's often nothing to do. The tissue is gone. You can't add it back. You may have just enough corneal thickness left to get by, or you may not. You're playing with a finite resource. Every one of these new approaches addresses that constraint differently. BPCDX adds real collagen-based tissue that integrates biologically. Precise Bio's bioprinted endothelium replaces cells that can never regenerate on their own. LASIK modifies refractive index without removing a single cell. Perfect Lens adjusts an eye's optics after it's been implanted for a decade. And the unanswered question? Implant synthetic stroma. Then ablate it to prescription. Would combine the first and second approaches into something that doesn't exist yet. The biggest barrier isn't the surgery. It's the collagen. Native corneal collagen fibrils are 25 to 32 nanometers in diameter. Center-to-center spacing, exactly 62 nanometers. 300 lamellae running in alternating directions through 500 microns of tissue. That structure is why the cornea is transparent. Current bioprinted corneas can get close on mechanical properties. They can't reproduce the fibrillar spacing at the nanometer scale. The Korean Postec group showed that shear forces during extrusion printing can partially align collagen fibrils. The printing process itself can begin to impose order. But it's a starting point, not a solution. The moment you implant a construct with imperfect fibrillar spacing keratocytes, The corneal stromal cells responsible for maintaining collagen architecture either remodel it correctly or transform into myofibroblasts and generate scar tissue. Which one happens depends on the mechanical environment, the surface chemistry, the degree of mismatch. Controlling that is the unsolved problem. 24 million Americans have cataracts. Hundreds of millions globally need refractive correction. The market for solutions that work better than cutting is enormous. The field has 3 parallel tracks running right now: cellular engineered implants, bioprinted living tissue, and non-ablative refractive modification. They're at different stages. BPCDX is the most clinically advanced with 2 years of human data. Precise Bio put its first implant in a human in 2025. LASIK is in European trials. None of them are available at your eye doctor yet. But the era of subtraction surgery for vision correction is ending. The next chapter is about what you can add, what you can modify, what you can print. The cornea is 500 microns of biological optical engineering. We spent 70 years cutting it. We're just starting to learn how to build it. 42 out.